Welcome to lecture 4.1 on college algebra on polynomial functions and models. Today, for a brief pause, I want to try a little experiment. So you might need to pause and do a little research in the midst of this. I want you to answer a few questions. What's a good guide for how much to spend on an engagement ring? Go ahead and hit pause now and use your phone and do a little quick Google search, or you may already know. I know that quite a few people do know, usually of a different gender. After you find that, how did you come up with that? Was it Google, and who was the source? Do you trust that source, etc.? So how did you find that answer? Did you just know it? Were you married? Are you married and used a guide for that? I know that there is a guide, kind of an industry standard is what they say. That sounds so official, etc. But now can you do a little more research and find out where that guide comes from? And it's been quite accepted in American culture to spend, or the recommendation is to spend 2 months' salary, and I don't know if that's gross or net salary, either way, on a diamond ring for an engagement. There was an interesting Netflix documentary, I believe, on De Beers, which is an older British family that controlled diamond mines in Africa for many years. And it's very insightful about how marketing influences us. And this whole made-up thing, notice what I said, made-up thing, about how much we should spend on an engagement ring has become part of our culture and part of our kind of common knowledge. And the fact that you have to buy a diamond for thousands of dollars versus cubic zirconia, which looks the same or similar. Even the fact of diamonds, it's just another stone on this planet. Why is it more valuable than, say, quartz, etc.? And so I think this is a good indicator in a lot of areas of our life about how we accept information without maybe validating information. And by validating, I mean, where does it come from, but also validating it for your own personal choices, lifestyles, and what's important to you, your values. So I want you to think about that, because this hits us constantly now with so much technology and so much social media and so many posts. I've personally turned the notifications off on my phone, so I no longer get news leads, Facebook updates, etc. I mean, I can check those. Yeah, I don't even get texts anymore because my phone was taking over. There's an old experiment on conditioning from, I believe, the 1950s or 60s with Pavlov was the scientist, and he had a dog, and every time he'd ring a bell, he'd give the dog a treat, and then he found out that if he rang the bell, the dog automatically started salivating. After a while, he had conditioned that dog to expect a treat when he got the bell. And there's a new documentary now, or well, it's new now in 2020, on called The Social Dilemma, and how our phones, Google, news feeds, Facebook, all use this same kind of conditioning response that make us basically addicted to our technology and reinforce our own beliefs, whether we've ever validated them before. So this is a huge caution in our lives about what's true, what's real. In a global way, what is really real? I mean, this idea about an engagement ring, I think, is a simple one without a lot of emotional attachment. So it's easier to look at without getting polarized, from different political parties, etc. But it's also about our own personal choices. Is 2 months' salary something you want to have on your hand? And I'm sure a lot of you are nodding, yes, I do. But when you think about the bigger scheme of things and where you want to be in life, where you want to be in 10 years, in 15 years, when you want to retire, the value of money, etc., this may be something different. So just a couple quotes here to finish this up. Be careful who you trust. Remember, the devil was once an angel. I like that one. And don't trust everything you see. Remember, even salt looks like sugar. So it's hard to kind of pick these things out when you've grown up with them or you see media advertising all the time. But I think it's really important and to pay attention to this. I know one of the first times this really hit me was I have 2 sons, and my youngest son was about 4 or 5, and we were watching TV, and a commercial came on for Life Takes Visa, and never really thought about it, never paid attention to it. But what it's saying, basically, the message behind that is, you're worthwhile. You shouldn't have to wait to have good things, so you buy them with Visa. And certainly followed that philosophy for a big part of my life. But when my 4-year or 5-year-old son turned around to me and said, "Can I have a credit card?" it kind of woke me up to like, wait, what just happened? And then I started paying attention. And don't forget that whenever you borrow money, you are cutting your future pay because you have to pay it back. And when you borrow money with a credit card, and whenever you use your credit card, you are indeed borrowing money at an extremely high interest rate. Most are over 20%. You are now cutting your future pay. You're docking your future pay. And if you're only paying a minimum balance a month, then you're doing it at a really high expensive rate. That Starbucks coffee that may cost $3 when you get to the counter, if you only pay minimum, by the time balances on your credit card, by the time you pay it off, that Starbucks coffee will now be $9, $10, or $11. Was that an expense worth it? Would you go in there and pay $11 for a Starbucks coffee? If you're not paying attention to the details, and if you're using credit cards so freely, then that is exactly what you're doing if you're not paying them off every month. All right, let's continue on. Today we're looking at polynomial functions and the models of their graphs. We're going to determine the behavior of the graph of a polynomial function using the leading term test. We're going to factor polynomial functions and find the zeros and their multiplicities, probably a new concept. And then we're going to solve applied problems using polynomial models. And this is one of the easier problems to solve if you know how to use your graphing calculator. So a polynomial function p is given by p of x equals a sub n x raised to the power of n plus a sub n minus 1 x to the power of n minus 1 plus a sub n minus 2 x to the power of n minus 2, etc., etc., till you get to a sub 1 x to the power of 1, or just x, or plus a sub 0. Where the coefficients are the numbers a sub n minus 1, a sub 1, a sub 0, etc. These are all numbers. They're multipliers in front. That's what a coefficient is. And the exponents are all whole numbers. In a polynomial function, notice that the largest exponent on any term is the degree of the polynomial. So in this case, n being the largest number in this kind of model, this would be a degree n polynomial, okay? And so that's the largest term. If a polynomial is written in proper form, it starts with the largest exponent and goes down to the smallest. Technically, even this last term, a sub 0, could be written as a sub 0 x to the power of 0, because remember, anything to the power of 0 is 1. So it also has an exponent on it. So constant numbers, constants, are a degree 0, because again we could write 4 as 4x to the 0 power. A linear function has a degree of 1. An example is f of x equals 3x plus 1. Notice the largest exponent on the x is a 1. Remember, we don't write a 1 exponent. A quadratic function has a degree 2. F of x equals 4x squared minus x plus 9. Again, the largest exponent is a 2. A cubic function has a degree 3. An example is f of x equals x cubed plus 2x squared minus x plus 11. Again, the largest exponent is a 3. And a quartic function has a degree 4. F of x equals x to the 4th minus 3.2 x cubed plus 0.1x. Again, our largest exponent is a 4. The coefficient in front of it is a 1. In the cubic, again, it's a 1. The coefficient in front, like the a sub n values. In our quadratic, the a is, or the coefficient is 4. In our linear, the coefficient on the lead term is the one with the largest exponent, is a 3, and our coefficient is a 4 for the constant function. So let's look at example quadratic function. We have a quadratic function f of x equals x squared minus 2x minus 3. We could factor this into x plus 1 and x minus 3. When we do that, we see that we have two zeros by setting each of the factors equal to 0, and we get x equals negative 1 and x equals 3. Remember, zeros are where a graph crosses the x-axis because the functional value, the y value, is 0. Notice these are also x-intercepts if I put them in coordinate form. The x value of the 0, comma, 0 for y. The x value of the 0, 3, comma, 0 for y. So zeros and x-intercepts are linked conceptually, but notice the answers are different. Zeros are just the x values. X-intercepts are points, so they have an x and y coordinate. The y-intercept we can see here is at 0, negative 3. Remember, you plug in 0 for x, 0 squared minus 2 times 0 minus 3 gives you negative 3. And we can see that on the graph where it crosses the y-axis. We have a vertex at 1, negative 4, and we've looked at those before when we did quadratics. And so we have a minimum value of negative 4, the y value, at x equals 1. There is no maximum because the graph continues to go up. And the domain is all real numbers because the graph continues to go left and right for all of x. And the range starts from the y value at the minimum or maximum and goes up to the infinity because it doesn't have an actual maximum. Remember, it goes from the y value to infinity if it's going up, or it goes from infinity down to the y value if it's a, it goes from, if it's a upward facing polynomial, it goes from the y value to positive infinity. If it's a downward facing polynomial, it goes from negative infinity up to the y value of the vertex, and we saw that in the last chapter. Again, we can see here that the quadratic function has an exponent of 2, and all quadratic functions are indeed degree 2. The largest exponent when written in standard form. Now this means that each of the terms are plus and minus. You don't have a factored form. So the degree of a function is the largest degree that's present when it's in standard form. Notice here, if it's in factored form, we could also find the degree if we thought about just multiplying all the x terms, all the factors, but the x is in there. And so we could see if we FOILed this out, we would get x squared, because there's x to the 1 times x to the 1, which gives us x squared. So you can kind of count the exponents on the factors, and we'll look at some of that in a minute. A cubic function, I'm not going to go through this one as well, but again, we have a cubic function g of x equals x cubed plus 2x squared minus 11x minus 12. You could factor this by grouping and get x plus 4 times x plus 1 times x minus 3, setting these all equal to 0. We get zeros at negative 4, negative 1, and positive 3. The x-intercepts again are points using these x values, and 0 for y. We plug in 0 for x and get the value of the y-intercept, which is negative 12. It's always the constant at the end. We have a couple relative minimums, or excuse me, we have a couple relative absolutes values, extreme values. We have a maximum and a minimum, a relative. Why do we say that? Why is it relative? Because notice the graph continues to go down to negative infinity, so there is no absolute minimum, and because the graph continues on to positive infinity, there is no absolute maximum. But in the middle of the graph, we can see like a little mountaintop here, which is a relative maximum, and we can see a relative minimum here where we have like a little valley. Again, the domain is all real numbers, goes from negative infinity to positive infinity, and in this case with cubic function it goes from negative infinity to positive infinity, so also the range is all real numbers. Again, we can see that the largest exponent is a 3 and cubic functions are degree 3. Let's look at some other examples of polynomial functions. F of x equals x squared plus 3x plus 1, a quadratic of degree 2. Here we have f of x equals negative 3. This is a degree 0 polynomial, again, because we could write negative 3 or 3 as 3x to the power of 0. We have a cubic function. Again, we can see that this is a degree 3. And we have a quartic function, which is degree 4. The largest exponent is x to the 4th. Okay. Notice the shapes of the graph and how they're different, and that's what we're going to focus on in just a second. The graph of a polynomial function is continuous and smooth. Okay. What I mean by continuous is that there are no x values where it doesn't have a value. It exists for every value of x. So the domain is always of a polynomial function, negative infinity to positive infinity. Okay? And that just means that the domain of a polynomial function is the set of all real numbers. Now, when we're talking about smooth, we're talking that there are no breaks, there are curves, but there are no corners, no hard edges, if you will, no quick turns. Okay? These are some examples of non-polynomial functions. On the left, you have h of x equals the absolute value of x plus 2. And right below it, you have h of x equals x to the 4/5. These are not polynomials because you can see in each of the graphs, there's a point or a hard corner. When you see a hard corner in a graph, you know that this is not a polynomial function, okay? Absolute value is not a polynomial function. And here, remember, polynomials have exponents which are whole numbers. And here we have a fraction exponent, okay? On the right side, we have h of x equals the square root of x plus 1 minus 1. And below that, we have h of x equals x plus 3 over x minus 1. In both of these cases, they're not polynomials because they're not continuous for all x values. If we try to find the domain here, we have to remember that x plus 1 has to be greater than or equal to, what's inside has to be greater than or equal to 0. So the graph has to be greater than or equal to negative 1. And we see that there are no values below negative 1. So this means it is not a polynomial because a polynomial is continuous across all of x. This is the same thing that we have in the bottom right graph, because notice when x equals 1, the denominator goes to 0 and the function is undefined. We actually have an asymptote here. And again, because it's not continuous, it is not a polynomial. This is a really important image for you to know and memorize. This is about how polynomials are shaped, really kind of largely at the outer edges of the graph, okay? So on your left here, we're talking about the degree. Is the degree of the polynomial even or is it odd? And across the top, we're talking about the leading term coefficient. Now this is the number in front of the variable with the largest exponent. And is it positive or is it negative? So when it's even degree and positive coefficient, we have basically a smile. It starts up and ends up. Okay, and you can see here's an example, 3x to the fourth minus 2x cubed. The a is a positive 3 and the degree is a 4. If the degree is even, but the coefficient is negative, here I have almost the same polynomial, but I have a negative 3 as the value of a, so it is negative, and we have basically a frown. And we saw this when we looked at quadratic functions before. Remember when a was positive, we got a smile. When a was negative, we got a frown. That gave us some insight into the shape of the polynomial or of the quadratic, whether it was pointing up or pointing down. Here we have 3x to the fifth minus 2x cubed. The degree is 5, and the a, or the coefficient, is positive 3. And this is what I call an S up. So when you have a positive odd, the graph is going up the entire time, sort of, at the outer edges. Not the entire time, because there's a lot of stuff that can happen here in the middle, like we just saw where there was a relative minimum and maximum in the cubic function previously in this lecture. And the last one is when we have a negative coefficient but an odd degree. This is a degree 9. The degree is odd and a is negative 3. And this is going to go down overall across the function. These little squiggly lines in the middle mean that you can have some maxes and minimums, ups and downs, peaks and valleys between the outer edges, which are going to go up for a positive even, down for a positive odd, coming from down and going up for an odd positive, and starting up and going down for an odd negative. The way I kind of remember this is that odd, which begins with O, begins and ends at the opposite direction. So it begins down, ends up, or begins up and ends down. Odd begins and ends in an opposite direction. So based upon that last graph, see if you can pause for just a second and play a little matching game, or I was going to say go fish, but this isn't go fish. Using the leading term test, match each of the following functions with one of the graphs A through D. So hit pause if you're ready to do this, and then see if you can match all these. So for the first one, 3x to the fourth minus 2x cubed plus 3, we have a degree 4, which is even, and we have the a is positive, so we have positive even, positive even. Well, remember, positive even creates a smile. Which of these graphs is closest to a smile? Well, that would be graph D. Degree 4, the coefficient is positive 3, and so we have, this is just telling you how to do that. Find the leading term, which was 3x to the fourth, and then determine the shape. For this first one, we had positive even, which is a smile, which would be a graph D. In letter B, we have negative odd. The degree is 3. The coefficient is negative 5. Now be careful. Don't always just look at the first term, because sometimes they'll be written in the wrong order. Like this could say negative x squared minus 5x cubed. Well, the 5x cubed would still be, the minus 5x cubed would still be the leading term because it has the largest exponent on it, even if it was written in the wrong order. So again, we have a negative odd. Negative odd gives us an S down, which is graph B. Remember, odd functions begin and end in the opposite side. Since it's negative, it's going to go down. It's going to go down from left to right. In C, we have positive odd. This is an S up, again, starting and ending in opposite directions. So this is going to be graph A. It's starting and down and ending up. And then the last one is negative even. We see it's a degree 6, and the coefficient is negative 1, so it's negative even, and we have a frown, and that is graph C. We can see it starts down and ends down, which is what a frown does. Okay, so you might want to review this slide again. This is a good insight. I also want you to see that there's all kinds of weird things that can happen in the shape in the middle. You can, again, have a valley and a peak, a relative minimum and a relative maximum. You can have something going on here, which I'm not exactly sure, must be going up and down. And even here we have some other kind of functions happening. we saw before that a 0 of a function is an x value that makes the y value go to 0, which is also related to the x-intercepts. So we say if c is a real 0 of the function, that is, that if we plug in x equals c into the function, we get a value of 0, then the point c comma 0 is an x-intercept of the graph of the function, and c, the x value, is called the 0 of the function. And it's a real 0 if it's a real number. We also have imaginary zeros. So let's find the zeros of f of x equals 5x minus 1 times x minus 1 times x minus 1 times x plus 2. We can rewrite this because we're not going to have three zeros that are equal to 1. We can rewrite this as 5 times x minus 1 cubed times x plus 2. To solve the equation, we want to solve f of x equals 0 when it's in factored form. We simply make each factor equal to 0. X minus 1 equals 0 when x equals 1. And x plus 2 equals 0 when x equals negative 2. And you could set these up simply. X minus 1 equals 0 and solve, and x plus 2 equals 0 and solve. Here's our graph here, and we can see that it has a relative minimum, and this is called a point of inflection. I think we're going to look at that in the next section. Notice again the relationships between the zeros of the function and the x-intercepts. The zeros are simply the x values of the x-intercepts, and x-intercepts are actual points on the graph, which must have an x and a y value. Okay. This is a really helpful feature if you're asked to graph a polynomial, and that is this characteristic called multiplicity. And this is based on when you have a polynomial in factored form. And so it's just saying if x minus c raised to the power of k has to be positive in order for it to be a polynomial. If it's a factor of the polynomial function p of x, and this is just saying, like in the last one, we wouldn't have said x minus 1 and x minus 1 and x to the first power. This is saying put it in its largest exponent. So instead of saying x minus 1 times x minus 1 times x minus 1, we would write that like we did in the last time, x minus 1 to the third power. So it's just saying that you recognize if there are multiple factors that are the same, that you're using the largest value of the exponent by combining them. X minus 1 times x minus 1 times x minus 1, those are all to the first power, is equal to x minus 1 to the third power. Okay? So if you have it in factored form, and the factor on the exponent, the exponent on the factor, not the factor on the exponent, the exponent on the factor, if it is odd, then the graph crosses the x-axis at that x-intercept. If the exponent on the factor is even, then the graph is a tangent to the x-axis, which means it touches the x-axis and bounces back on the same side. Okay, let's look at this graph. This graph has three zeros. We can see it's crossing at -3, -1, and at x equals 2. These are the three zeros of this function. Since it crosses at x equals -3, it crosses over x to the other side, and at -1, it crosses over x to the other side. We know that the multiplicity is odd for these two values, or these two factors of the polynomial. Since it touches and bounces back to the same side at x equals 2, then we know that the multiplicity is even. And I just wanted to show you what that looked like. So the multiplicity was odd at -3 where it crosses, it's odd at -1 where it crosses, and it's odd at it's even at x equals +2 because it touches and bounces back. Now, if we looked at a function that this might represent, we can see that if these are the three zeros, we know that we have x plus 3 as a factor, because this equals 0 when x is negative 3. We can see that we have x plus 1 as a factor because that equals 0 when x equals negative 1. And we can see that our third factor would be x minus 2 because that equals 0 when x equals 2. Okay, that's how we found zeros. Notice the exponent on the negative 3 factor, or negative 3, 0, is a positive 1, which is odd. Notice the factor on the 0 at x equals negative 1 is a 3. Again, it's odd. So at both x equals negative 3 and x equals negative 1, we would expect the graph to cross over x and continue on. X minus 2 factor, or x equals 2 is the 0, has a factor of 2, which is even. So when we get to that point, when our graph is coming to that 0 at 2, it's going to bounce back to the same side it was coming from. Okay? And so I wanted you to see how this works. What you're doing is you are, to find the multiplicity, you must have it in factored form, and then you're looking at the exponent. You're looking at the exponent on each parenthesis or factor. Now be careful because 0 could be an intercept for some functions. 0 is an x-intercept for some functions. And if that was the case, you'd also have another factor out here that would be just by itself, for example, x. And if it was x squared, then it would bounce back because it would be an even exponent. If it was x cubed, like for example it said 4x cubed here, then we know that at 0 it would cross over because the exponent 3 is odd, and that means it's going to cross over. This is again another important thing for you to see and know to be able to graph whether a graph is going to cross the x-axis at the 0 or whether it's going to bounce back. It crosses when it's odd and bounces back when it's even. Okay, so when it's odd, it continues on to the opposite side. Odd goes on to the opposite side, like we saw with the general shape. So let's find the zeros of f of x equals x cubed minus 2x squared minus 9x plus 18. Here we want to put this in factored form. If we group the first two terms, x cubed minus 2x squared, and we group the second two terms, 9x plus 18, we get this first diagram. But wait, notice we no longer have plus 18, we have minus 18. Well, why is that? Well, when we group these two last terms, and if there is a minus in the middle, then we have to change the operation between those two last terms. Why? Because of distribution. If we took the parentheses away, remember this would be minus 9x. Okay, that's right. Minus a minus 18 is plus 18. So this is a really important rule to remember when you're factoring by grouping, that if there's a minus between the two parentheses, you must change the operation from plus to minus, or from minus to plus, whatever it was, change it to the opposite when you add the parentheses because of distribution. We then do some factoring out. We can factor out x squared in the first term. We can factor out 9 in the second. And now we see we have a common term of x minus 2 that we can factor out of this first term and the second term. And we get x minus 2 times x squared minus 9. Well, x squared minus 9 is the difference of squares. And this is equal to the sum and difference of their square roots. So we have 3 zeros. We have a 0 at 2. At negative 3, and at positive 3. Okay, these are our zeros. Another concept that can kind of help us is to figure out how many x-intercepts are possible, and also how many peaks and valleys. Here we have a valley, and here we have a peak. You might think of these as maxes and minimums, etc. The total number of peaks and valleys is on the graph of a polynomial function of degree n is at most n minus 1. So the number of peaks and valleys is 1 less than the degree. So if this is a degree 3, then at most I could have 2 peaks and valleys, and that's what I have here, 1 and 2. Okay? The number of x-intercepts is at most the same as the degree. So x-intercepts is the same as the degree. Maxes and minimums, or peaks and valleys, the most you can have is one less. Okay, so the peaks and valleys is less than or equal to one less than the degree, and the x-intercepts is less than or equal to the degree. It doesn't have to be equal. So if you have a degree 2 polynomial, which is a quadratic, you could have 0 x-intercepts, 1 x-intercept, or 2 x-intercepts, okay? It can be less than or equal to the degree. All right, let's look at these and see if you can figure out, again, you might want to hit pause, based on each function, what is the degree of the function? What is the maximum number of peaks and valleys, which again, remember, is one less? And what is the number of x-intercepts from a maximum perspective? Okay. So again, in this first one, we have a degree 3, the largest exponent. The maximum number of peaks and valleys is 2, and the maximum number of x-intercepts is 3. In the second one, we have a degree 5. So the most maxes and minimums we can have is 4, and the number of x-intercepts is equal to that degree. Now this is weird because notice the number of x-intercepts changed, okay? So here we have a degree 4. This actually has 3 peaks and valleys. What this is actually telling us is the actual number of x-intercepts. So I wanted to include that, even though it's not the maximum number. I wanted you to see that it doesn't have to equal. In this specific graph, there are only 2 x-intercepts. It could have up to 4, but it only crosses the x-axis twice. Okay? The max would be 4, and this last one is the same. We have a degree 6. Here we only had 3 peaks and valleys. We could have had up to 5. Here we had 2 x-intercepts, and we could have had up to 6. So I wanted to show those 2 examples where the numbers could be different. They don't have to be one less. That's the maximum they can be. In the last example is a great example where you see we only have 3 peaks and valleys and 2 x-intercepts. So look at this graph up here. Based upon the x-intercepts, if the degree was either 2, 3, 4, 5, 6, or 7, what possible degrees could this graph be? Okay, so the first thing you want to do is to think about the shape of the graph. What does that tell you about the degree? What does that tell you about the degree? And then once you have the degree, that concept of the degree, what do you know about peaks and valleys and x-intercepts? Okay. Well, notice that we're starting up and we're ending down. We're starting and ending at opposite sides of the x-axis, which means that our degree is odd based upon the shape. So immediately we can get rid of 2, 4, and 6. So we know we have either a 3, a 5, or a 7 graph. Okay? The number of x-intercepts is 1, 2, 3. So the degree of the polynomial can be, remember that the x-intercepts is less than or equal to the degree. So since I have 3 x-intercepts, I could have a degree 3 polynomial. I could also have a degree 5, because degree 5 can have 5, 4, 3, 2, 1, 0 x-intercepts. And a degree 7 is the same. It could have 7 x-intercepts, 6, 5, 4, 3, 2, 1. So the number of x-intercepts tells us this could be 3, 5, or 7. Well, what about, let's check the peaks and valleys. This has to be one less, okay? So since I have 1 valley and 1 peak, I have 2 total. So the degree would again start at 3, because the degree is going to be 1 more. And so in this case, the peaks and valleys also tell me that I could have 3, 5, or 7. So the degree of this could be any of those, 3, 5, or 7, based upon the shape we know it was odd, and then based upon the number of peaks and valleys or x-intercepts, we could see it was possible to be any of those odd functions. Let's look at one more example here, and this is really based upon some suggestions about using your calculator. Most of these problems are pretty easy to solve. Students get them wrong because they try to enter it into their calculator every time. And this is, kind of a painful thing to enter into your calculator. The polynomial function m of t equals 0.5 t to the fourth power plus 3.5 t cubed minus 96.65 t squared plus 347.7 t. This can be used to estimate the number of milligrams of pain relief medication ibuprofen in the bloodstream t hours after a 400 milligram of the medication has been taken. Find the number of milligrams in the bloodstream at t equals 0, 0.5, 1, 1.5, and so on, which means 2, 2.5, 3, 3.5, etc., up to 6. Round the function values to the nearest tenth. Well, that's probably about, 12 or 13 different values I have to figure out. If I'm going to try to enter this in each time, 0.50 to the fourth plus 3.50 cubed, and then do it again, 0.5 to the fourth, etc. It's likely that I'm going to make some mistakes. So what you want to do here is to use your calculator, use the y equals function, and plug in this as a formula, 0.5 t to the fourth or x to the fourth plus 3.5, etc. Because once you've entered this into your calculator in the y equals function, you can go back and double check. Did I get each one of the right? Is the coefficient right? Is the exponent right? Is the plus and minus right? Etc. And then you can simply use the table function. You're going to have to change the delta x value because your table normally shows whole number values of x, 0 or 0, 1, 2, 3, 4, 5, 6. So where it says delta x, which is a little triangle x, put in 0.5 there, and then it'll give you values every 0.5 units. When you do that, you're going to get these values rounded. I'm not going to go through all of these, but it's much easier to then look at all those values and then enter them into your test or homework, etc. And then this is a graph of this polynomial function. And we can see that we're getting the maximum dose. This is kind of interesting. Ibuprofen is a form of aspirin, right? Or a headache medicine or fever medicine. So it looks like our maximum effect, the maximum dosage in our blood, the maximum concentration, comes right after 2 hours. And then it pretty much all dissolves 6 hours later, so it's only useful. This is a 400 milligram dose. So you can see how this actually works for polynomials. This is just the same thing, and so we're at the end of our lecture. Reach out if you need help, and be thinking about that diamond ring. I'm telling you, be careful of marketers, be careful of commercials, be careful of not paying attention to TV. You can start adopting thoughts and practices that really aren't in your best interest. And all I'm saying is make sure you know where ideas come from and if they make sense for you, just because someone tells you. And who's telling you to spend 2 months of your salary on a diamond ring? Diamond companies, because that benefits them, not you. All right, have a good week, and I'll reach out if you need me.